I had to.
Welcome everybody to our Gamma seminar. Today we have the pleasure to guest Manuel de León from the CSIC and Real Academia de Ciencias de España. So, Manolo, thank you very much for accepting our invitation. It's a pleasure to have you here to talk about new geometry structure in thermodynamics. This is a cool topic and we look forward for it. So, please, the floor is yours.
Thank you. Thank you very much, Javi, and thank you for the invitation. I will try to don't see the number of slices because it's not. I will not use all the slices. This is just a presentation to show how we can use more general geometric structures to describe thermodynamics. Usually, I will give some ideas. Uh, uh, as all of us know, symplectic geometry is the framework to develop time-independent mechanics, co-symplectic geometry for developing time-dependent mechanics. We have some dissipation, not all the dissipation, but some special kind of dissipation. We use contact geometry. And this contact geometry is used traditionally in the description of the the equilibrium states, equilibrium thermodynamics, and the the equations in thermodynamics are interpreted as the local equations of a Legendrian submanifold. Uh, Most of you know that time-dependent and time-independent mechanics use the Hamilton principle. Contact geometry use the Herglot the Herglot principle, and we will see how one can use calculus of variations to obtain the equations for more general thermodynamic systems, that is equilibrium systems. And this has been done by Gable, Math, and Yoshimura, and they obtained the equations using a rational principle, and we will recover these equations by Gable, Math, and Yoshimura using geometry. And this is important because if you have a geometric description, you can apply well-known tools in geometry mechanics to study these systems, symmetries, reduction, and so on. And so, in a simple thermodynamic system, we have, and this is the reason to use contact geometry. You have the volume, the pressure, and the temperature. And also we have the properties of the gas described by a two-dimensional submanifold in a thermodynamic space of dimension 5, for instance, R5. We have also the energy and the entropy and the volume, pressure, and temperature, five variables. And the energy, the entropy, and the volume are called the extensive variables, traditionally in thermodynamics, and temperature and pressure are the intensive variables. And you can see that you construct this contact form on R5. You can see that the energy, depending on the entropy and the volume, is just described by these equations. And this is just a Legendre submanifold of this contact manifold R5 with this 1 for eta.
Manolo.
And there,
Manolo, sorry.
yes.
One curiosity, because I've been doing this stuff lately, and instead of the energy, I was using other functions, for example, enthalpy or things like that, in which instead of the entropy and the volume, I used other variables that are just manifold, for example, the T or the P or whatever as new
Yes,
variables.
you can
Have you
change.
seen
You
that?
can change the variables. You can change the variables, but at the end, more or less, it's the same scheme.
Yeah, I know, but
Because you
physically,
have five. Yeah, but
the thing, man.
the basic parameters are temperature, energy, pressure, volume. This is for gases, for instance.
Mhm.
And so
Okay,
these
okay,
are the usual applications.
Thank you.
Okay. And in these two papers with Alessandre Simoes, David Martin, and Manuel de León, we developed this scenario, and I will show you some of the results in these two papers about this description of thermodynamics using contact geometry. And in a more recent paper with Jaime Bajo, we obtained a description of the rest of thermodynamic systems, those considered by Guy Balmaz and Yoshimura, but introducing a new geometric structure we call partially cosymplectic. And now in this preprint that practically is finished, it will be in archive very soon, in a few days. We apply this geometric interpretation just, for instance, to develop geometric integrators and to discretize the system. So this is the main novelty the main novelty to that we get just from the geometric description. And so the people use different geometric structures. For instance, this so-called metripletic structures are very popular. In these two papers, Morrison is one of the founders of this metripletic framework. And this consists in a Poisson structure and a gradient structure. So we have a metric and a gradient an additional function, and the entropy is constructed as a Casimir or the Poisson structure. So you can see in these two papers, there are many papers with studying these metripletic structures. And there are other approaches. For instance, this by Edwards and Beris is a similar technique, but it is called single generator formalism, because they introduce a bracket divided into parts, a non-canonical Poisson bracket and a dissipation bracket. And so, well, this is a way to deal with more general thermodynamic systems. And this is just the paper by Gabe Almaz and Yoshimura. And this contact structure, by the way, Javi, this was developed, this contact approach by some Polish mathematicians. Rugala is one of the
Yeah,
main
I know there are a couple of famous
researchers
papers
in this
in
area.
yeah.
Yes, yes, yes. He worked a lot in this contact approach. And there are more approaches. This by Valiant and Valentin, and this by Van der Schaaf and Maskey, based on homogeneous symplectic Hamiltonian systems. And this is a paper by Arjan van der Schaaf introducing a new geometry we call Liouville geometry. Liouville geometry because it's based on the canonical Liouville form on the cotangent mandel. And even more, Arjan van der Schaaf has also developed these Port Hamiltonian systems to deal with thermodynamic systems. And so I will recall some well-known notions on contact dynamics. We have a contact manifold with a contact one form, the red vector field. This isomorph is defined from vector fields to one force. Uh, and so we have a Darboux theorem, and you can find these coordinates Q, P, and S, such that the one form is written in this normal form, and the Liouville vector field the red vector field is just the partial with respect to S. We can define by vector lambda using just the differential of the contact form, and we can define this mapping from one form to vector fields, and even more, giving any function, you can construct several two vector fields, two different vector fields. The Hamiltonian vector field, define it in this way, using these mappings. This is the local expression of the Hamiltonian vector field with Hamiltonian F, and the evolution vector field, which has a modification of the Hamiltonian vector field using the red vector field. And this is, at the bottom is the local expression of the evolution vector field. And also we can prove that any contact manifold is a Jacobi manifold, defining this this bracket of the functions. And this is a Jacobi bracket. This is not a Poisson bracket because it does not satisfy the Leibniz rule. And this is the local expression of this Jacobi bracket for this contact for the contact manifold. And we can introduce another bracket, which is called this lambda is just the part defined by the differential of eta. You will remember this here. This lambda is just the differential of eta with a sign minus, but is strictly is these two tensors. And so this is the expression of this bracket. We call Cartan bracket. This bracket don't satisfy the Jacobi identity. So, well, if we can consider the cotangent bundle of the conformation manifold Q, we have this canonical contact structure, differential of S minus the theta Q is the Liouville canonical form on T star Q. And so we construct this one form eta Q, and eta Q is a contact form. This is the local expression. So we can define another by vector lambda naught, which is just this lambda plus we use the coordinate S and the red vector field, and this is Poisson. So we have we are in a contact manifold, but we have a Poisson tensor, which is the canonical Poisson tensor on T star Q, considered in R times T star Q. So we have the Cartan bracket. You can be written in this way using this lambda naught tensor. This delta is the Liouville vector field, the usual Liouville vector field, and so we can prove that this Cartan bracket is a sum of the bracket defined by lambda naught and the bracket defined by delta in this way. Well, this is not important. Also, we can do the same in the Lagrangian setting. I will skip this because it's the same thing. We construct we assume the Lagrangian irregular, and we can consider the construction of the symplectic form, the one form and the symplectic form, and we are in R times TQ, so we can construct the corresponding contact form on TQ times R, or R times TQ is the same. And we can also have the Legendre transformation, and so we can move, we can compare or transport things from the Lagrangian to the Hamiltonian side, and from the Hamiltonian side to the Lagrangian side, because the energy can be defined in this the classical way: momentum times velocities minus the Lagrangian. Okay, so this is the questions for this standard the evolution vector field for a Hamiltonian function H. And this is interesting because we can see that the energy is constant along, it's not constant along the Hamiltonian vector field because we had a dissipation, but the evolution vector field is preserved by the evolution vector field, and also this is another property applied to S, is just delta applied to the energy.
One Manolo, one question, because I didn't see much of it. Normally in contact geometry you have knot theory, yeah, for Legendre submanifolds. Do you have anything like that in thermodynamics or have been used?
Yeah, well, I will go to this point later.
Okay, wonderful.
Now we will have these things. So if a Hamiltonian come from a Riemannian metric
Mm-hmm.
G,
Mm-hmm.
we have some potential P depending on Q, and the S will be the entropy. So we can prove these two properties. The Hamiltonian is preserved along the evolution vector field, as we show before. And this is the first law of thermodynamics. And the second law of thermodynamics is the evolution of the entropy is delta applied to H, and this is greater or equal to zero, which is the second law of thermodynamics. So we can prove in a very simple way using contact geometry. Also, we can express these things in terms of the brackets defining the evolution of any observable, and well, these are things that happen in contact using this contact geometry. And of course, in the Lagrangian, in the Lagrangian side, we obtain this. Well, this I think that this is not necessary to. So this is just a way to show how the the evolution of the entropy is related with some friction in the system. So I will skip this because it's not the most important thing. Okay, so we consider this now more general systems, and you remember that the first equations, the evolution vector field has if you integrate the evolution vector field, you obtain the equations, the thermodynamic equations, and they represent a Legendre submanifold in the corresponding contact manifold. But there are systems, a more general systems. For instance, systems that are adiabatically closed or with several entropy variables, not only one entropy, several entropies. Systems that can exchange heat, or systems that can have matter with the stereo. So these are more complicated systems, and so this is just the idea of Gabriel Mata and Yoshimura, just to using a variational principle, they obtain the equations for these more general systems. And the idea was how to recover these equations, but from the geometry, not using a variational principle. And so we introduced this partial cosymplectic structure. Remember that a cosymplectic structure is given by a pair of a two form and a one form, closed two forms, omega and eta, such that omega n times wedge eta is a volume form. So the manifold has dimension 2m plus 1. And of course, there is a Darboux theorem, and you can find coordinates q, p, and theta. We have the red vector field. And if you have a Hamiltonian, you can consider different vector fields. For instance, the gradient of the Hamiltonian is just using this isomorphism from tangent to cotangent bundles of the manifold. We also have the Hamiltonian vector field and the evolution vector field. But these are not exactly the same thing that in the contact case, because this is a different geometry. And remember that I can obtain the Hamilton equations or the Lagrange equations in the cosymplectic setting using the Hamilton principle. But in the contact case, I had to use the Hertog principle. So they're different, also they're different geometries. And so this is the local expression of the evolution vector field in this cosymplectic case, and this just gives the evolution of the Hamiltonian, and you can consider the Hamiltonian formal is on the cotangent bundle times R, so we'll consider this star Q times R, and we define this is the usual Liouville one form, but consider it on the product of T star Q times R. And of course, the symplectic form of T star Q can be considered on the product of R to T star Q because it's just the pullback with using the canonical projection, well, and so on. So you have Hamiltonian, you have these three vector fields associated to the Hamiltonian. And also we have the same for the Lagrangian formalism. The Lagrangian is defined on TQ times R, and we can construct this lambda L is just the one form defined in the usual way, but now consider it on TQ times R, so it's the pullback to TQ times R, or the form constructed on. So it is not right. So we consider S, S is just the canonical endomorphism, the vertical endomorphism, or the canonical almost tangent structure on TQ, and you can extend to TQ times R in a trivial way. So this is because L is a function on TQ times S, not in TQ. Okay. So it is lambda L, and we have the usual local expressions. If the Lagrangian is regular, then omega L d zeta is a cosymplectic structure. We have the red vector field and the three vector fields associated to the Lagrangian are just the gradient, the Hamiltonian vector field, and the evolution vector field. Okay, and this is just the expression, and you recover the integral cubes of the evolution vector field are just the solutions of the Lagrange equations. So this is the Legendre transformation. So it's the same, and we maintain this parameter zeta. Okay, and we define the energy in the usual way. We assume that the Lagrangian is hyperregular to have a global diffeomorphism. If not, we have only local things. But well, we can show that we can prove that both descriptions are equivalent through the Legendre transform. Okay. Now, to go further, we need to introduce semi-basic forms. This is very well described, the use of semi-basic forms in the book of Godvillon. In the last chapters of Godvillon, he considered the forces as semi-basic forms. So this is the usual way to put forces in the system. A semi-basic form, which is just a form which vanishes on the vertical vector. So in the tangent bundle, you have coordinates q dot. The one form has the components depending on q and q dot, but only have components in the dqs, and in the I think this is a mistake here. No, it's okay. It's in the cotangent bundle is depend on q and p, and of course we can consider also semi-basic forms on depending on time, so or depending on the parameter s. In our case, will be the entropy. It's in the q times r on t star q times r. So one force that vanishing on vertical vectors with respect to the informations over q times r. So we have the similar expression, but in this case we have an additional parameter zeta on the components of the semi-basic force. Okay, so these are the expressions. So if you have, for instance, the cosymplectic formulation, and we add a semi-basic form, you have to put apart from the differential of the energy and the d zeta, we have to put this force in the equation. So you obtain the local equations. and with an additional term, just the term given by the form. In semi-basic, so it don't affect to the equation because it's only the components will be a part of the equation, but the equations are exactly the same plus these forces. Okay, so we introduce this generalization of cosymplectic structures, almost cosymplectic. Of course, we know that an almost cosymplectic structure is a manifold with two forms, omega and eta, such that omega n times which eta is a volume form, and if omega and eta are closed, we have a cosymplectic structure. If omega and eta are not closed, so we have an almost cosymplectic structure. And but we can consider the situation where the two form is closed, but not the one form. And we call these structures partially cosymplectic. And by the way, this was introduced earlier by José Janisca and Marco Moduño in a paper in Journal de Mathématiques Spirit Appliquées. And they consider just this kind of structures, partially cosymplectic structures. In particular, if you have a contact manifold, the differential of eta is closed because it's a SAT, but eta not, it's not closed. So the eta is a partial cosymplectic structure. So it's something more general than contact structures.
Manolo, apart from
Even
the fact that it is, Manolo, sorry, apart from the fact that it's more general, they had any other motivation for doing so?
yes, we will see just the motivation right now.
Okay.
Just immediately. Even if there is a partially, it's not eta is not closed, we can obtain a red vector field. It's the same definition. Of course, we don't have Darboux coordinates because eta is not closed. But we can define the similar things to the cosymplectic and the contact case. We can define the evolution vector field for any function in this way, because this mapping from vectors, tangent vectors to covectors, this bemol, is an isomorphism. So if you have f and we consider the differential of f plus eta, we obtain a vector field, and we will call this vector field the evolution vector field. And so this fulfill the needs for some systems, but not for all. For all, we have to introduce a generalization of this partially cosymplectic structure. We call in this paper, Union Physics A, we call almost cosymplectic structure of order P, partially cosymplectic structure of order P, and in this case, omega is a two form, and we have a family of one forms in such a way that this is a volume form. The dimension is 2n plus p. And of course, if omega is closed, we will call this partially cosymplectic structure for the p. But the etas are not closed. And we can do the same. We don't have a red vector field, we have a family of red vector fields, define it in this way. And for corresponding to any of these one forms. And of course, we can also define an evolution vector field because we have this isomorphism bemol, and we can consider external forces F in addition. So we have the evolution matrix defined by df plus eta minus the external this force F, which in our case will be a semi-basic one form, but not now. Okay, so these are not. So, for instance, this is the reason to introduce these systems, these structures. Consider adiabatic closed simple thermodynamic systems. We have a configuration manifold. We have a cotangent bundle, we have the entropy of the system, and we consider T star Q times R. And we consider Hamiltonian defined on this manifold, and we consider semi-basic force. Fs represent the external force acting on the system, and Fr is the friction force acting on the system. And so these are the local expressions because R is semi-basic. We are now in T star Q times R. And we define this one form, eta. And we have a two form, and the two form is just the pullback of the canonical symplectic form on T star Q. So we have one of these structure. This is this omega and eta is not closed in general. So we have a partial ecosymplectic structure. And we can consider local coordinates. We don't have the root coordinates, but we are in T star Q times R. So we have coordinates Q's, P's, and the coordinate S. And so we can do that. And so we obtain the evolution vector field. This is the form of the evolution vector field. Well, we obtain in the usual way the components of the evolution vector field, and we now we can consider the integral curves of this evolution vector field. And we have these equations and this equality. Of course, if the Lagrangian, if we have a regular Lagrangian and the Hamiltonian comes from this regular Lagrangian using the Legendre transformation, so we can move everything to the Lagrangian side. Remember this equation: the partial of S with respect to S is just minus partial of L with respect to S. S is a global coordinate. And we define this, we transport everything to the Lagrangian side, and you have this eta L, omega L, and so on. So we have all these things. And we can consider the evolution vector field for this partial cosymplectic structure. Omega L is closed because it's a SAT, but this eta L is not closed. But even so, we have the relation between the evolution vector fields from in the both sides. And we can consider the corresponding, I will call Euler-Lagrange equation, but it's something more general. And if we look at the equation, we just obtain exactly the same equation that Guy Balmat and Yoshimura have obtained in his papers. And so this is a way to define, to obtain the thermodynamic equations using geometry. Of course, in this case, one can recover the contact thing using some friction force defined that to take into account this dissipation. But in general, and this is another step in the in the plan, is just to consider, for instance, the second step, systems with internal mass transfer. So these systems, one can imagine that we have internal compartments, K internal compartments, and a compartment has nk particles. We can think, for instance, in a gas with different compartments, and the number of particles is nk. And now we introduce this manifold Rk, and representing the number of particles in each compartment, in compartment K, also in the corresponding compartment. And we have the change of matter, and we can consider the entropy of the system. Now we have one entropy, S. And so this is our system. Is T star Q times P1, remember that P1 is RK, P2, remember that P2 is again RK, times R. And we can pull back the canonical form on T star Q, so we obtain the two form on M, and also we consider this semi-basic one form representing the friction and the external forces. which locally will be represented in this way. Well, so this is just a function that introduced the Kaibalmata and Yoshimura. Just is there functions on n, which is without this one or this rk, but it's just some functions satisfying some properties. And we consider this one form. And so we have the same thing. We have this WK are coordinates on one of this P2. Is P2. And so we can consider this form. So it's not the form T-star Q plus is the canonical form T-star Q, the pullback, plus this additional form. Of course this is closing, which it is a SAT. And so we have again a partially cosymplectic structure, and we can consider again all these local expressions, and we can obtain the evolution vector field. We do the same thing just to obtain the Lagrangian, and changing from the Hamiltonian side to the Lagrangian side, we have exactly the same equations obtained by Gaibalmata and Yoshimura. Another system is more complicated. It's a diabatically closed non-simple dynamical system. This means that we have per-simple subsystems, and each of one has its own entropy. As A is the number of the A is the label for any of these simple subsystems. And so we can do the same. So the procedure is very simple. It's just to start with the cotangent bundle of Q. Q is the configuration, mechanical configuration manifold, and we add this R. So now it's more complicated. Every time we have more factors. But we do the same, exactly the same thing, and we again obtain the equations obtained by you can go to the paper of Guy Balmat and Yoshimura, you get these equations. And even another system, open simple thermodynamic systems. In this case, we have more complicated. We have the number of moles of the because we have different chemical species in one compartment, and so we have again we can consider these external forces and friction forces, and so we define these functions, and this with the molar flow rate. Well, there are these physical quantities that are interpreted by these functions, and so we do the same again, because the trick is that you always have T star Q. And so we obtain exactly the same, the equations obtained by Gevalmat and Yoshimura. So now, and I don't put more slices, more slides. Sorry, I will always say slices, and it's not a pizza; it's slides. We are just in this prepping. We develop for the more simple system, the vertical closed system, because for the rest is will be more or less the same, but more tricky, it's not so clear like in the first case. So we developed the discretization, a discretization of the system with a proper discretization. We obtain the discrete thermodynamic equations. We study symmetries of the system, and also we develop the usual way, geometric integrators, and we have some simulations just to show how these things work. So this is the main thing that we can. You have this geometric description. You can go to the tools in geometric mechanics just to apply to these things. For instance, discretization. And so in the future, we are trying to develop brackets, reduction, symmetries, and so on in this abstract setting, and then apply to the thermodynamic things. So this is the prepping that will be. Asier is attending the talk, so we hope that this will be in archive probably next Monday or Tuesday, and we
Hopefully,
are
yes.
continuing to hopefully yes. Okay, so I think I stop here and thank you for the attention.
Thank you, Manolo. Thank you very much for a nice talk. So, is there any question, remark, comments? Okay, so I have many. Manolo, which approaches are very modern lately? Because you said about 13 approaches to thermodynamics that they were very old and on the metaplate or something like that. What is going on now?
Yeah.
A part of your paper, of
Well,
course.
yes, this indeed, there are many approaches. Thermodynamics is a very intriguing issue. It's not easy to work with thermodynamics, and people don't like to work with thermodynamics. I know people in continuum mechanics, and for instance, in the constitutive relations of the body, you can put temperature and entropy. People don't like because it's complicated. But
Mm-hmm.
the idea was how to obtain these equations in the more simple way. We
Mm-hmm.
don't have to introduce Casimir generating functions, and so a very simple geometry. And in this case, is you have a two-form and one-form, and semi-basic one-forms representing the forces. And with these notions, you can obtain any equation, any thermodynamic equation. So this is just the idea behind our approach. So well, I think that one interesting thing will be also to compare with the previous approaches but continuously appear new things. I read recently a paper trying to obtain the thermodynamic equations using symplectic geometry. This is not the right way because this is not symplectic, but
You know that saying the right way can be tricky.
yeah,
But I understand what you mean. Just a curiosity, Mano, because we just published, sent to the archive a paper about fluid hydrodynamics and thermodynamics for fluid dynamics, yeah? Or in field theories in relativistic hydrodynamics.
yeah,
And it took people less than 24 hours to send us an email about it. Was
yeah,
kind of
yeah,
shocking. I mean, we have generated this with K-contact geometry to field theories, to thermodynamical system and hydrodynamic equations. It, I could say that people are interested in that part. At least it seems that it's cool. This is the comment. At least
yeah.
physicists. The problem can be about the mathematics that they don't like much to get
Yes,
involved.
yes, yes,
And
yes.
it
Yeah,
it indeed, Manolo, which topic do you think that it can be more applied, more interesting in this
well, I think that
for
one
physicists?
important thing is that if you develop a geometric description of any physical phenomena, you had to be able to do something. So in this case, we can discretize and obtain numerical integrators. So
Mhm.
this is okay. So you are of course people can read the paper or not. I remember that the paper we published with Jaime, it was immediately accepted. So we revised little things, and
Mhm.
they were very enthusiastic in Journal of Physics A with the paper because it's a fresh approach.
Mhm.
Uh,
Oh, I understand.
so
And
this is my you also have to maintain the contact with reality. You can develop many fantastic mathematical theories, but these theories have to be some physical counterpart. If you
it's
want to apply to physics, you have to 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 take you have to take account of the physics involved, not
I have another question because I was thinking of many things about all of it, but I didn't know if someone has done it. Because, for example, I was thinking of using canonoid transformations for contact geometry in thermodynamics. Do you know if anyone has tried to do so?
yes, I read something, but I don't. Well, I was not interested, so
Hmm.
for the
But there
moment,
is
so I
you saw that something there is something about that. Okay, so for
yes,
me it's okay,
yes,
Manolo. Mhm.
yes, I remember that the canonoid transformation was very interested. There are some papers some years ago by Pepin Cariñena and other people. This canonoid
Indeed.
transformations in mechanics.
He
Yes.
was very interested in it. That's more or less why I'm asking because of that, because he said me about this topic. Okay, for me it's okay. Is there any other question?
Well, I have a couple of side remarks. I think this approach of understanding entropy as a Casimir, the first to introduce it was Jean-Marie Souriau, the French mathematician. And how you were saying that that this metriplectic is very old, and it is true, but as far as I know, there are still papers being published last year about it. So this
Yes,
That,
yes, no,
approach
that,
seems to still be alive.
there are many
that,
people.
that, that's the point. That when Manuel said that there are a lot of works, I didn't know whether these works are all or there is something going on that's still in the topic.
Yes, yes, I remember also a very interesting PhD thesis directed by Ernesto Lacomba.
Hmm.
One of his students did a very interesting thesis using contact geometry and Riemannian geometry, but it's not well known. So that it's very appealing to because in in thermodynamics you have the natural thing is to think in a contact structure because you have the variables there. So, so it's very so immediately
Natural, yeah.
you consider the natural. Now it's more it's just to extend this idea to a more general things. Of course, we have to introduce this standard and friction forces. This is, but this another thing is that if you look in the samples in the dynamic systems, you find pistons. Thermodynamics is the science of pistons. So these are the samples.
Mhm.
A piston in a cylinder with gas. All the samples are more or less variations of this of
Cool.
this.
In this case.
But they are very
Okay. Yeah.
interesting because
Yeah.
now one can
This is
imagine
what.
a gas and you are in a piston. The gas is exerting some friction force, and so this is interesting.
Okay. Is there any question, remark?
Yes, I do have one. Could
Yeah.
you say something more about, I mean, I understood that your approach retrieves the well-known equations in thermodynamics, but do you know if your geometric approach gives more geometric insight into the theory?
Yes,
Could you
because
provide some examples?
yeah. Well, the first thing is just to develop this discretization in the usual way. So, and we are trying to do more things to study reduction procedures, brackets, what are the submanifolds in these cases, what kind of submanifolds can be defined. So, and one idea is that you have a very good classification of submanifolds, like in the contact on the symplectic case, you could you are lucky you can identify the equations as a submanifold of some type, something similar to the Legendre submanifolds in the contact case. Should be different, but we can think in this. So the geometry will give you new ways to study the dynamics.
Thank you very much.
Well, any other question?
Yes, I would have a question. You've mentioned that we would use the structures to describe more complex thermodynamic systems, but there are still some open problems like open thermodynamical systems. Do you have any idea if someone is working on that, or are there any ideas which geometrical structures we would use to describe that, or is it possible?
Well, this partially cosymplectic structure was just defined by Janiska and Modugno many years ago. I forgot because they wrote a book about quantization and they used these cosymplectic things. And Marco Modugno wrote me an email many years ago, and he told me, well, because I met in several conferences. And I met him several conferences, and I insisted him to call these things cosymplectic. And so he uses these cosymplectic things. But this is introduced in this generalization is in our paper. Our paper was published in March, I think, paper with Jaime, and we sent the papers I think just at the end of December to Journal of Physics A. But well, this
Okay,
is
thanks.
one can use these structures to apply to, for instance, in our case, to thermodynamics, or to use to study these structures in geometric for pure geometric interest.
Okay. Any other question? No. Then thank you very much again, Manolo. It's been a very interesting talk, very nice. And we'll see you in a week. The speaker will be Michał Grunland from the University of Montreal, and he will talk about hydrodynamical systems. And thank you very much, Manolo, again, and see you in a week. Bye.
Yes, I will remain because Xavi